Hey guys, and welcome back. And today we're going to be talking about how to convert decimals into fractions and fractions back into decimals. Our learning target today is to convert rational numbers. Okay, I'm going to explain what the word rational means. We're going to convert those rational numbers from fractions to decimals and decimals into fractions. So obviously, there are going to be certain types of numbers we can consider rational. Our success criteria today, we're going to convert a terminating decimal into a fraction. Okay, so we're going to need to talk about that word terminating. We're going to be able to convert a repeating decimal into a fraction. Okay, so we're going to have to distinguish the difference between something that terminates and something that repeats. And we're also going to convert fractions into decimals by performing long division, which you should have already done a warm-up with me practicing how to divide two numbers. So the key idea here, I'm not going to read this whole big paragraph. You can if you like, but really what this is saying is a rational number, root word ratio, is a number that can be written as a fraction. Okay, so that's what I'm going to write down here in our language. Can be written as a fraction. There are certain numbers that cannot be written as a fraction. There's no possible way to convert them into a fraction. So any number that can be written as a fraction is considered rational, even if it's not a fraction to start. For instance, if I have 25 cents, that's 0.25. 0.25 is 1/4 of a dollar. So really, 0.25 is the decimal version of 1/4 as a fraction. So this number would be considered rational. The whole number 5. Any whole number can be written over 1 because anything divided by 1 is itself. So that's also can be written as a fraction, the number 5. Okay, so we're going to talk about what to look for on how to recognize what a rational number is. The first one that we're going to recognize is if it's a terminating decimal. So I'm just going to put a synonym for the word terminate. Terminate. That means to end. Okay, so something that does not go on and on forever. If you've ever noticed, if you type certain numbers in your calculator, the entire screen gets filled up. Well, that means that the numbers don't stop, that they could go on and on and on forever. So in these examples, these are all decimals that terminate, they end. There's no numbers that come after, like with 9/5 that equals 1.8. There's no numbers that come after it. So really, we can put zeros. Okay, you've learned in the past that there are an infinite amount of zeros before and after each number. Okay, well, if there's any zeros to the right of a number, that means it has ended. Okay, so I could write more zeros on all of these, but the zeros to the right of every significant digit is not necessary. Okay, so to distinguish this between a terminating decimal and a repeating decimal, as you guys can see, these numbers repeat off to infinity and fill up your calculator screen. And instead of writing a lot of 3s, okay, I just want you to write it with a bar over the number that is repeating. Okay, and I only want you to write the bar over the number that's repeating. Like in this example, I do not put the bar over the 4 because there's only one 4, whereas the 6s are repeating off into infinity. Difference between that and something like this, I can see the pattern goes 4, 8, and then starts to repeat 4, 8, 4, 8. So I would extend the bar over both the 4 and the 8. Okay, so two rational identifications when you're looking at decimals, terminating or repeating. So let's try the first example. It says, Allen wrenches are often needed to assemble furniture. One commonly used size is 3/16 of an inch. What is 3/16 written as a decimal? So this is kind of like the warm-up we did. A fraction written as 3/16 is the same thing as if you were to write 3 divided by 16. Or long ways, 3 divided by 16. Remember, whatever is doing the dividing goes on the outside, and whatever is being divided goes on the inside. Or the numerator is on the inside and the denominator is on the outside. So since 16 is bigger than 3, I'm going to put the decimal place to the right of the 3. which means I can write an infinite amount of zeros that come after that. Okay, I'm only going to write 1 for now and see where that gets me as far as how many times 16 can go into now, and I'm going to ignore the decimal place right here. How many times 16 can go into 30 evenly, as in a whole number. And I know that if I were to do 2 16s, that's actually 32. So I'm only going to put 16 into this once, and I'm going to subtract it from 30. Well, 30 minus 16 is 14. So you ask yourself, can 16 go into 14? Okay, nope. Whole number will not come out if you do 14 divided by 16. 14 is smaller than 16. So I'm going to grab another 0. I'm going to bring it down. And now I'm going to take a guess at how many times 16 can go into 140. Well, I know 16 times 10 is 160. So if I take away a 16, that's going to be about 144. If I take away 2 16s, that's going to be even less. So I'm going to guess 8, because 10 minus 1 is 8. So now I am going to do 8 times 6, which is 48. Carry the 4. 8 times 1, which is 8, plus 4 is 12. So 16 times 8 is 128. I'm going to subtract that from 140 and get 12. I'm going to grab another 0, pull it down. Now I have to know how many times 16 goes into 120. So the last number I guessed, which was 8, was 128. So if I take away another 16, that'll definitely be smaller than 120. So I'm going to guess 7. 7 times 6 is 42. I'm going to carry the same 4. And then 7 times 1 is 7, plus 4 is 11. 120 minus 112 is 8. Grab another 0, carry it down. How many times does 16 go into 80? I'm going to guess 5. Okay, so I'm gradually pulling it down. 5 times 6 is 30. And then carry the 3. I just write the 3 right over my previous number. And then 5 times 1 is 5, plus 3 is 8. And 80 minus 80 is 0. I actually ran out of room on my screen. Actually, I'll pull it down and show you guys. 80 minus 80, which is 0. That means I'm done. Once I get a remainder of 0, I'm done. That means the decimal terminates. Okay, so it ends after 5. So my decimal here is 0.1875. I won't even require that you write that leading 0. You could just write your answer just like this, without the leading 0. So let's have you give this long division a try. You've done long division before, it just may have been a while, so if you need to, re-watch the process or raise your hand and ask a question if you need guidance. Go ahead and try this. You try. You're trying to convert 5 30-seconds into a decimal. Alright, so in the second example, I just want to compare numbers in different forms, either comparing two fractions, two decimals, or a fraction and a decimal. So let's first look at letter A. I want to know, are they equal or not equal? Well, in order to be able to do this, we need to convert any and all fractions into decimals. So I'm going to do my long division work, 5 divided by 9. So for my first number, 9 goes into 50. Let's see, the closest number multiple of 9 is 45, which is 9 times 5. So 50 minus 45, that gives me 5. Now, if I were to drop down another 0, I just get 50 again. And then I'll end up saying that 9 times 5 is 45 again, and I'll end up getting 5 again. So this is indicating to me that this is 0.5 with the 5s repeating. So I can say that 5/9 is the same as 0.5 repeating. So since the 5's repeat off, I can say that these two numbers are equal. Sorry about that. So now I'm going to do the same thing for B, C, D, E, Okay, so now I want to kind of go over my calculations with you guys and make sure we all understand why I wrote either equal or not equal on these. All right, so obviously if you see the same exact number written down, it's equal. So 0.5 repeating is equal to 0.5 repeating, excuse me. But then for 7/6, that was equal to 1.16 with the 6 repeating, which is exactly the same as what is written on the other side, so it's equal. If we look at the next one, I did 1 divided by 11 over here, which I have the 0.9 repeating. And if you think about what each side is saying, 0.0909 off to infinity, this one is actually saying there are zeros following all of this, or there are zeros following the 9 all the way to infinity. So that means if we compare, the zeros are the same, the 9's are the same, the zeros are the same, but then right there, the 9 compared to the next 0, 9 is bigger, which makes it not equal. Same kind of deal over here with 13 over 5. That was just equal to 2.6. 2.6 with a bunch of zeros to follow it. Whereas this one is 6's all the way to infinity. So this 6 is equal to this one, but then 0 is less than this 6 right there, which makes them not equal. For D, I saw the same exact thing written. If I just put that negative sign on the number, it's the same thing. So those two are equal. And then my last calculation I did down below, I got 1.6 repeating, which means those 6's will go off to the end of your calculator. This 6 is equal to this 6, but then this 6 is not equal to the 7 that is there. And that's not to say that it's rounded, so these are two different numbers. Okay, so just saying whether they're equal to each other, being able to compare decimal places. Why don't you guys give this a try in your second U-Try? I want you to take 3/9 and turn that into a decimal. Alright, so now we're getting to a little bit of a process here. The introductory for how to do example 3 is on this slide. It says recall that all repeating decimals are rational numbers. Okay, we have done long division to get repeating decimals, but how are we supposed to find a process to change those repeating decimals back into fractions to show that they are rational? You can use algebra to actually do this. So let's say you have n equals 0.72 with the 7 2's repeating. So that number really is 0.727272, and it'll keep doing that. Whenever you see those 3 decimal places, those 3 dots at the end, that means etc. or the pattern continues. Okay, so what you do is you think about how many digits are repeating, and that's the power of 10. So number of digits is the power of 10. Now what I mean by power of 10 is like 10 to the first power is equal to 10. 10 to the second power, or 10 squared, is 100. 10 to the third power is 1,000. So however many digits are being repeated is the power of 10 you should multiply each side by. So there are 2 digits repeating in 0.72. So we picked 100 because 100 is 10 to the second power. When we do that, whenever we multiply by tens, however many zeros there are, that's the amount of spots the decimal place moves over to the right. So it's kind of like we're taking this decimal and we're going 1, 2 when we multiply it by 10, thus making the number 72.72 repeating. So we come up with this equation right here. Okay, we have a new equation that's multiplied by 100. If we take the original equation, we said n was equal to 0.72 repeating, and we subtract it, that actually makes the repeating decimal become 0. Even though it goes off forever to infinity, you're still subtracting itself, so it becomes 0. It's like 72.0 at the bottom. So really, now I'm just solving for n. If I divide both sides of this equation by 99, I get 72 over 99, and then that reduces. Both the numbers 72 and 99 can be divided by 9 to simplify this fraction. So the fractional version of 0.72 repeating is 8/11. So I can say that these two numbers are equivalent to each other. Okay, it's like writing in two different languages in math. The fraction language, or the ratio language, and the decimal language. But they mean the same exact thing. Now I'm going to show you guys this one more time, actually 2 more times in this example. That means you're going to have 3 different references to be able to try this on your own. And yes, it is difficult, so make sure you're paying attention and you're asking questions when you need them. Let's try A. The first thing I want you to do is write an equation with this number equal to the variable. So let's call the variable x. X is equal to 0.4 with the 4 repeating. Create an equation first. Now multiply each side of the equation by the power of 10 that matches the number of digits that are being repeated. Okay, well, there's only one digit being repeated. 10 to the first power is just 10. So I'm going to multiply both sides of this equation by 10, giving me 10x is equal to, now when I multiply the decimal by 10, it's like we're moving the decimal place over 1 spot. Okay, 1 spot because there's 1 0 in the number 10. So now this becomes 4.4 repeating. Okay, if you can't imagine where that came from, think of what 4 repeating means. So 0.4 repeating means 0.4, 4, 4, 4, 4 off to infinity. If I move the decimal place over 1 spot, that means I get 4.44444 off to infinity. So I'm just now, instead of writing the 4s, I'm writing 4.4 repeating. So now I'm at this point. I want you to rewrite your original equation. Okay, the equation, all you did was set the number equal to a variable. I want you to rewrite that equation below your power of 10 equation. And I want you to create a giant subtraction problem from it. Because when you do that, the 4 repeatings become 0, and you're left with 4 minus 0, which is 4, equals, and 10x's minus 1x. Remember, when we don't have the number, when we just have a variable, the number 1 is really written next to it. So 10x's minus 1x, that's 9x. So when I solve for x here, I divide by 9 on each side, and I get x is equal to 4/9. So 4/9 is equivalent to the decimal form 0.4 with the 4 repeating. Those are equivalent to each other. I'll give you one more. Now with 2 digits. So again, my first step was to call the number a variable, make an equation out of it. There are 2 digits repeating here. 10 to the second power is 100. So I'm going to multiply both sides of the equation by 100. That's 100x is equal to 100 has 2 zeros in it, so I'm going to move the decimal place over 2 spots, which means I get 45.45 with the 45 repeating. I'm going to rewrite the original equation underneath my new one and make a giant subtraction problem out of these two. The 0.45 repeatings go away. 45 minus 0 is 45. Drop down the equals. 100 x's minus 1x is 99 x's. And then divide by the number multiplying x. We get x is equal to 45 over 99. I should try to see if I can reduce that. Both 45 and 99 are divisible by 9. So that means my fraction is 5/11. 5/11 is equivalent to 0.45 with the 45 repeating. So 3 different times I have put repeating decimals into fractional form. That is proof as to why these fractions are called rational for ratio. Let's have you give this a try in your third U try. I want you to put both of these numbers in fraction form. I've got 2 last questions for you. Please reread these again and ask for help if you don't understand what the questions are asking you. These last 2 questions are just to push you a little further and see if you truly understand what we were doing in today's lesson when we were converting decimals into fractions and fractions into decimals. Go ahead and try to give these a shot. Alright, so that wraps up our lesson on converting rational numbers from fractions into decimals and vice versa. We did our success criteria a little out of order. Number 3, success criteria, converting fractions to decimals. We did that in the warm-up. And we also did that in example 1 and example 2. For converting terminating decimals into fractions, we did that in example 2, and we did the repeating decimals in example 3. So please make sure you can go in and out of the 2 different forms, decimals and fractions. Go ahead and give your homework a start and make sure you go back and rewatch anything that you didn't understand and ask questions when you need to. Thanks. Have a great day.